So friends, over here today we will learn about group theory, and this is especially helpful to all those students who are doing their masters in chemistry or are going to do their masters or are just here for a quick revision. So we will look into the concepts in a brief manner, but we'll be solving all the type of questions that come from group theory. So this will be around a three video series lectures, very short videos, mainly discussing the type of problems, so that whatever kind of problem comes, you know how to approach it in the right way. So let's get started with that. So in group theory, we have the symmetry elements, Cn, which is the proper axis of rotation, sigma reflection, I for inversion, Sn for improper axis of rotation. And so, as you know, of rotation means it rotates the molecule. We won't get into the details, but just the basics to brush you up if you are not, if you have forgotten all these things. So n. So what is n over here, right? So suppose there's a 120-degree rotation of the molecule. Okay, 120-degree rotation of the molecule. In that case, n is equals to 360 by 120, which equals to 3, meaning it's a C3 rotation, right? So n gives us the order. So sigma is a reflection, it reflects the molecule, and sigma square. So if you reflect the molecule 2 times, it gives you the same molecule, right? Sigma can be in 3 parts. Sigma h. Sigma h is the one which is perpendicular to Cn. Sigma v, which is in the axis of the Cn, and sigma d, which bisects the two adjacent C2 axes. Okay, we don't really need much of this. Okay, and over here we have I, which is the center of inversion, and Sn is the improper axis of rotation, which is actually Cn, and then a reflection which is perpendicular to Cn, right? Cn is a rotation, and then the reflection has to be perpendicular to that rotation. And so I have given you some very tricks and traps that are actually asked in exams to confuse students. So in Sn, the n can be odd or even. If the n is odd, right, as for let's say S3, it requires 2n operations to reach the exact identical configuration or to be equal to E, right? So if it's a S3, it will require 6 operations. And if Sn and n is even, suppose S4, it will just require n number of operations. So it will just require 4 operations, as in S41, S42, S43 and S44 to reach E, or the exact identical configuration. Do remember that identical and equivalent are not the same things. And over here we also have Cn, that if n is odd, Sn will contain a Cn, right? But if n is even, Sn will contain a Cn by 2. Okay, so these are actually very much asked in exams. So we also know that S1, it is C1 then sigma, which actually gives us the sigma, right? And S2 is C2 then sigma, which actually gives us I. So both sigma and I are actually contained inside Sn axis. And this is a simple operation of S32, and how it operates I have just shown you, right? Sigma square is E. C infinity, what is it? So what is C infinity? So suppose we have a 0-degree rotation, right? So in that case we will have our n as infinity, and an example of this is in CO2. If we pass the axis from this in this way, C infinity axis actually exists, and they also have infinite C2 axis. Now, using our knowledge, the main application of this knowledge is actually in the finding out point groups, right? So this is the Schonfeld's notation of finding out point groups. So first over here, suppose we are checking for whether the molecule is linear or not. If the molecule is linear, like CO2, does it have I? CO2 does have I, so it will be in D infinity H. If it does not have I, it will be in C infinity V. Suppose it's a non-linear molecule like trans N2F2. We have to see whether it has sigma. If it has sigma, it will be CS. This is only for when Cn, n is more than 1. It does not have n more than 1. So the maximum it can go is C1, right? So if it has sigma, it will be CS. If it does not, it will be Ci or C1. And if it has I, it is Ci. And if it does not have I, it will be C1. And for molecules with N more than 1, we have the following, just wait, part, right? And so for molecules with N more than 1, we check whether it has C2 perpendicular to Cn, in particular NC2 perpendicular to Cn. If that is the case, that it actually has NC2, n number of C2s perpendicular to Cn, there will be in the D point group, and if it does not have, it will be in the C point group. Within the D point group, we first check for sigma H. If it has, it's DNH. If it does not, it's DN or DND. If it has N sigma D, it will be DND. If it does not, it will be DN. Similarly for Cn, we first check for S2N because it's an a specific case. We just check for S2N whether it's there or not, and if it is, then it's S2N. Otherwise, we go for the similar checks. We check for sigma H and then sigma V. Just say in the same way as we checked for sigma H and sigma D for the D groups. So having known this, we find out the point group of the molecules. So over here we will learn all the examples that are given for different point groups. So the main problem that's given is to find out the point group of a molecule, right? So suppose for C1 over here we have, it's a point group for which there is no symmetry element as such. This is the E, which is the identity, right? So over here we see they have all different ligands, right? So they have no symmetry element as such, and this belongs to C1. For a simple molecule which has just sigma, suppose for SOCl2, right? There's just a sigma between it, so it will have CS pointing group, right? And for a molecule which has I, suppose this molecule they have given, and over here we see it has I over here, center of inversion. This is if this is a point, so we reach the same ligand from this side as well as this side, same ligand from this side as well as this side, so we can say it as I and it's a Ci point group. A molecule which has just like H2O2 gosh or a cis, so if we have CO and this is En, so suppose a nitrogen bidentate ligand and Cl over here, so it's cis, and we can have a C2 point group over here, as we can well see that if we rotate it by a 180-degree rotation, we can get an identical operation, right? And similarly for a bidentate ligand having 3 times, so AXY whole 3, right? It's a bidentate ligand occurring 3 times. So suppose A is over here and X, Y, X, Y, X, Y, right? So if we can have C3 rotation as in 120-degree rotation, and we will have it in an identical way. Similarly for H2O, it has both C2 and sigma V, right? H2O, it has two sigma V's, or two sigmas basically, because we have a C2 over here and as well as a plane, we can say, separating it, and as well as a molecular plane, right? Having this molecule intact. We also have C3V as for NH3, similar to H2 only, except the difference it has a C3 instead of C2. So these are just famous examples, that's why I'm showing it to you, right? NH3 and so this is actually a pyramidal shape, right? And for C4V, this we actually have square pyramidal molecules which actually take IF5 XCF4, which actually take the CF4V point. So it is actually a trick you can use. From the VSE pair theory, you can find out the structure and then just find out the point group. And trans N2F2 is a very famous example of C2H, right? So trans N2F2 has in this molecule. It has C2H, right? So it has both I as well. Remember this. You can see easily it has I, same ligand from this side as well as this side. And H3BO3 or boric acid as an example of C3H, a very important example. And now we come to some a bit more complex ones over here. So we have over here C2H6, which is ethane gauche, which takes a D3 point group, and as well as C2H6, which is ethane in the eclipsed form, which takes a D3H point group, and the ethane, so I'm just marking it, okay, C2H6 having the ethane in gauche form taking D3, ethane in eclipsed form taking D3H, ethane in staggered form taking D3D form, okay. I'm just marking the famous examples, so you can just practice for homework and see it for yourself, okay. And we have borazine, which takes the D3H point group, and the famous example BF3, right, which takes the D3H point group. Do see it for this one. It's a very simple one, and you can have a lot of your doubts cleared from this one. And ferrocene in the eclipsed form takes the D5H point group, and it's not, I think, given over here, but the ferrocene in the staggered form takes a D5D point group, okay. The benzene takes DCH point group. The cyclohexane in the chair form takes the D3D point group, and methane takes tetrahedral and SF6 takes octahedral point groups, right? These are some linear systems. As I said, these take the C infinity H and C infinity V and D infinity H point groups. So this was the application part of the knowledge we learned before, and you have to see it for yourself, practice for yourself. I have told you the famous examples as well. So, and obviously famous example of diborane, which I missed out, which takes the D2H point group, right? So just see it, and once you have seen all these examples, and you can take a screenshot as well of all the things I've shown you, and it'll be very simple to you, right?